Hello everyone. This is our lecture series on database management systems, paper code EC703C. And in our last lecture, we were going through normalization. We will continue our journey with normalization. We have seen extraneous attributes and their effects on our database design. We will continue with that. So in today's lecture, our outline of today's lecture will be algorithms. First, we will go through some algorithms for decomposition using functional dependencies. Then we will see multi-value dependencies, what they are and how to decompose a given relation using them. And we will see domains, atomic domains, what are they, and first normal form. Then the whole database design process and how to model temporal data. So this is our lecture plan today. So let's move forward. So we will begin with algorithm for decomposition using functional dependency. We will start with a procedure to test for BCNF. BCNF we have studied in our previous lectures that it is Boy's code normal form, and it is a very popular normal form which eradicates a lot of problems present in a bad database design. Now we will see a procedure to test if a given database is in BCNF or not, right? So the procedure is as such like this. Now to check if a non-trivial dependency alpha implies beta causes a violation of BCNF, we first compute alpha plus, which is the attribute closure of alpha, and we verify that it includes all attributes of capital R, that is, it is a super key of R, right? Then we apply the simplified test. So this is, see, first we are trying to find if any non-trivial dependency alpha implies beta is causing some violations of BCNF. Then we are computing alpha plus, that is a closure, attribute closure of alpha. We know that how to find out attribute closure. First we find out the extraneous objects and all. Then we need to verify that it includes all attributes of R, that is, it is a super key of capital R. So the simplified test procedure is like this. To check if a relation schema R is in BCNF, it suffices to check only the dependencies in the given set capital F for violation of BCNF, rather than checking all dependencies in F plus, that is F closure. So it suffices to check only the dependencies in the given set F for violation of BCNF. So we don't need to check for all dependencies. We just need to check the dependencies in the given set capital F. No need to go for F plus. That is the closure, F closure. If none of the dependencies in F causes a violation of BCNF, then none of the dependencies in F plus will cause a violation of BCNF either. We can prove that. That if we can prove that none of the dependencies present in capital F causes a violation of BCNF, then we can also prove that none of the dependencies present in F plus will cause a violation of BCNF either. Right? Now, the simplified test using only capital F gives us incorrect result when testing a relation in a decomposition of R. Suppose let's take an example to clarify this. Suppose R equals to A, B, C, D, E, with F having A implies B, BC implies D. Now we decompose R into R1 having AB and R2 having A, C, D, E. Now neither of the dependencies in F contain only attributes from ACD, so we might be misled into thinking that R2 satisfies BCNF, right? But the dependency AC implies D, as we can see in F plus, shows clearly that R2 is not in BCNF, right? So we are trying to decompose R into two new relations, R1 and R2, one having AB, another having ACDE. Now, neither of the dependencies in F contain any attributes, contain only attributes from ACDE. So we might be misled into thinking that R2 satisfies BCNF. But we can clearly see that R2, because of the presence of AC implies D, we can say that R2 is not in BCNF. Okay, moving forward. Now let's check an testing algorithm for BCNF decomposition. Okay. Now either test Ri for BCNF with respect to the restriction of F plus to Ri, that is all FDs in F plus that contain only attributes from Ri. So either we don't need to test for all the relation. So we either need to test for Ri with respect to the restriction of F plus to Ri, that is all functional dependencies in F plus which contain only attributes from Ri, or we can use the original set of dependencies capital F that holds on R, but with the following test. That is, for every set of attributes alpha as a subset of Ri, we need to check that alpha plus, that is the attribute closure of alpha, either includes no attribute of Ri minus alpha or includes all attributes of Ri. So for every set of attributes alpha, which is a subset of Ri, we need to check that alpha plus, that is the attribute closure, either it includes no attribute of Ri minus alpha or it includes all attributes of Ri, right? So if this condition is violated by some alpha tends to beta in F plus, the dependency alpha implies alpha plus, that is the closure of alpha minus alpha intersection Ri, can be shown to hold on Ri, and Ri thus violates BCNF. And we can use this above dependency to decompose Ri. So the procedure is again just to summarize. We need to test either for Ri with respect to the restriction of F plus to Ri, or we can use the original set of dependencies that hold on R, but we need to consider this, that for every set of attributes alpha is, which is a subset of Ri, we need to check that alpha plus either includes no attribute of Ri minus alpha or includes all attributes of Ri. Now, if the condition is violated by some alpha implies beta in F plus, then the dependency alpha implies alpha plus minus alpha intersection Ri can be shown to hold Ri. So this is the second procedure, and thus we can confer that Ri violates BCNF. Okay. So moving forward, this is the same algorithm just written in the pseudocode. So we are taking a variable result. We are initializing that variable with the given relation R. We're checking one variable, John equals to false. Now we compute F plus, that is the set of functional dependencies. Now while not done, do if there is a schema Ri in result that is not in BCNF. Okay, so if there is a schema Ri in result that is not present in BCNF, then we begin that let alpha implies beta be a non-trivial functional dependency that holds on Ri. So we are beginning the process here, that we are letting that alpha implies beta is a non-trivial functional dependency which holds on Ri, such that alpha implies Ri is not in F plus, that is the F closure, and alpha intersection beta is null. That means alpha and beta, they are not sharing the common attributes. Then result, the variable result becomes result minus Ri union Ri minus beta union alpha beta. Right? And if there is a schema Ri in result that is not in BCNF, that means any such Ri, if we can found them, then the process ends. And if that is not so, then we are just changing the value of the variable done to true, and we can surely say that each Ri is in BCNF and our decomposition is lossless join. Okay. Now here is some example of BCNF decomposition. Class having course ID, title, department name, credits, section ID, semester, year, building, room number, capacity, time slot ID. So these are the attributes of class. Given the functional dependencies, course ID implies title, department name, and credits, and building, room number implying capacity. We can see that course ID, section ID, semester, year implies building, room number, and time slot ID. So for the class relation having three functional dependencies, let us see how we can decompose it. Now the candidate key is course ID, section ID, semester, and year. The BCNF decomposition is giving us course ID implies title, department name, and credit. But course ID is not a super key, right? The super key is the candidate key is course ID, section ID, semester, and year, and we can clearly say that course ID is not a super key. And if it is not a super key, then we can replace class by two new subclasses or sub relations, course and class 1. Course having course ID, title, department name, and credits. Class 1 having course ID, section ID, semester, year, building, room number, capacity, and time slot ID. Fine. So we are replacing our main relation by two new relations, course ID, title, department name, and credits, and course ID, section ID, semester, year, building, room number, capacity, and time slot ID. So we are decomposing the given class relation into two new relations, course and class 1. Now, course is in BCNF. Of course, how we can be sure about it? Because building and room number implies capacity. This holds on class 1, but building room number is not a super key, right? So we replace, see, for course, we can surely have course ID as the primary key. But here, building room number implies capacity, holds on class 1. But building room number is not a super key for class 1, the new relation class 1. So we can replace class 1 by classroom and section, again two new relations. So we are again building two new relations, classroom and section. Classroom having building room number and capacity, section having course ID, section ID, semester, year, building room number and time slot ID. Classroom and section are in BCNF. Fine. So building room number implies capacity holds on class 1. Now we replace class 1 by classroom and section. And now we can see that though class 1 doesn't have a super key, and that's why the class 1 was not in BCNF. We are replacing class 1 by classroom and section, and we can see that classroom and section are in BCNF. Now to move on, we will test our dependency preservation algorithms on 3NF, third normal form. Now, because there are some situations where BCNF is not dependency preserving and efficient checking for functional dependency violation on updates is important. That is, while doing the updates, we need to check for functional dependency violation. The solution is to define a weaker normal form, or a normal form which has less stringent rules, called third normal form. Now this allows some redundancy. With resultant problems, we will see some examples. But functional dependencies can be checked on individual relations without computing a join. There is always a lossless join, dependency preservation decomposition into 3NF. Right? So we're allowing some redundancies, but functional dependencies can be checked on individual relations without computing a join. Now there is always a lossless join, dependency preserving decomposition into 3NF. Now, if we want to test that if a given relation is in 3NF or not, let's take this example. The relation name here is department advisor, having three attributes: SID, IID, and department name. And the functional dependency SID department name implies IID, IID implies department name. The two candidate keys, SID department name and IID SID, are given there. So the first candidate key comprises of SID and department name, and the second one have IID and SID. Now R is in 3NF. Clearly we can see that. And we can say that SID department name implies IID SID, and department name is super key. But IIG implies department name. Here department name is contained in a candidate key. So having two candidates key, SID department name and IID SID, we can see that R, the given relation, is in 3NF because of the two functional dependencies, the first one and the second one. And the first one, department name is super key, and in the second one, it is contained in a candidate key. Now, how to test for 3NF? We need to check only functional dependencies in F. We need not check all functional dependencies in F class, that is F closure. Okay, we can use attribute closure to check for each dependency alpha implies beta if alpha is a super key. If alpha is not a super key, we have to verify if each attribute in beta is contained in a candidate key of capital R. So if alpha is not a super key, we have to verify if each attribute in beta is contained in a candidate key of capital R. Now this test is rather more expensive since it involves finding candidate keys, and testing for 3NF has been shown to be NP hard. Now what is NP hard? NP stands for non-polynomial. There are some algorithms which can be solved in polynomial time. We will study this, or I don't know if you have studied algorithm design and analysis of algorithm, that paper, and you already know that how to find out NP hard, that is non-polynomial hard. It is now it is proved that testing for 3NF is an NP hard problem, right? That's why we will look for a different way to find out if decomposition into 3NF can be done in polynomial time. So we'll look for another procedure. So this is the Sage algorithm. So let FC be a canonical cover for F, where initializing I with 0. Now for each functional dependency alpha implies beta in FC, we do if none of the schemas are J, 1 less or equals to J less equals to I contains alpha beta, then we begin by I equal to I plus 1, Ri equals to alpha beta, and we end the process there. If none of the schemas are J, where 1 less equals to J less equals to I contains a candidate key for R, then we begin I equal to I plus 1, incrementing the value of I. Ri is any candidate key for R. We're taking any one candidate key for R. Optionally, we can remove some redundant relations. So what we are doing, first we are taking functional dependency alpha and beta from FC, that the closure. And if none of the schemas are J contains alpha beta, then we begin by I equal to I plus 1, Ri equals to alpha beta. If none of the schemas are J contains a candidate key for R, okay, if none of them contains a candidate key, Then we begin by I equal to I plus 1 incrementing. And then Ri equals to any candidate key for capital R. Now, if any schema capital Rj is contained in another schema capital Rk, then Rj equal to R, I equal to I minus 1, and we return R1, R2 up to Rj. So let Fc be a canonical cover for F. Now for each FD's alpha implies beta, if none of the schemas Rj contains alpha beta, then first we begin with having Rj's and then we insert alpha and beta into them. Now if none of them contains a candidate key, then we again are supplying candidate keys from R to Rj. Now this procedure is repeating, right, until all the functional dependencies in F closure has been taken care of. After this loop exists, then we are checking any schema Rj is contained in another schema Rk. Then Rg becomes R, I equal to I minus 1, and we are returning all the relations, that is after decomposition, the results that we are getting R1, R2 up to Rj. Okay. Now this algorithm is not a NP-hard algorithm. Here each relation schema Ri is in 3NF. The decomposition is dependency preserving and lossless join. The proof of correctness is at the end of this presentation. We will check. I will give you some materials for that. Now, let's check one example from our previous given ERG diagram, and let's see how they work. Now, relation schema, customer banker branch, which has customer ID and employee ID as primary keys, and branch name and type. The functional dependencies for these relation schemas are customer ID, employee ID implies branch name and type. Employee ID implies branch name. Customer ID branch name implies employee ID. So we first compute a canonical cover. Where branch name is extraneous in the right hand side of the first dependency, and no other attribute is extraneous. So we get FC equals to customer ID, employee ID implies type. Employee ID implies branch name. Customer ID branch name implies employee ID. Okay. Now the for loop in our previous algorithm, we'll generate the following schemas: customer ID, employee ID, and type, the first one, employee ID branch name, the second one, and customer ID branch name, employee ID, the third one. Now you can observe that customer ID, employee ID, and type contains the candidate key of the original schema. So no further relation schemas needs to be added. So the for loop generates following 3NF schema: customer ID, employee ID, and type, employee ID branch name, customer ID branch name, employee ID. Now you can observe that customer ID, employee ID, and type contains a candidate key of the original schema. So no further relation schema needs to be added there. Okay. Now at the end of the for loop, we are detecting and deleting those schemas such as employee ID branch name, the second schema, which are subsets of other schemas. And the result will not depend on the order in which functional dependencies are considered. You can take any order. You just have to make it sure that all functional dependencies present are being taken care of. After detecting and deleting the schema, the second schema, that is employee ID branch name, the resultant simplified 3NF schema is customer ID, employee ID, type, customer ID branch name, and employee ID. So we are getting two relations from the given relation customer, banker, branch. So it is being decomposed into 3NF decomposition into two new sub relations: customer ID, employee ID, type, customer ID branch name, employee ID. Now here is a comparison between BCNF and 3NF. So it is always possible to decompose a relation into a set of relations that are in 3NF such that the decomposition is lossless, the dependencies are preserved, and it is always possible to decompose a relation into a set of relations that are in BCNF such that the decomposition is lossless, but it may not be possible to preserve dependencies. So see the subtle difference that we can decompose a relation into a set of relations which are in 3NF such that the decomposition is lossless and the dependencies are preserved. Right? That is for 3NF. And for BCNF, the decomposition is still lossless, but it may not be possible to preserve all the dependencies, all the functional dependencies given, or the F closure given. So that is the difference between BCNF and 3NF. Now here's the design goals. We will move forward to actually how to design relational databases. The goal for a relational database is BCNF, having BCNF, lossless join, and dependency preservation. If we cannot achieve this, then we accept 3NF, where there is a lack of dependency preservation and a little bit of scope of having redundancy due to the use of 3NF. Now, SQL doesn't provide a direct way of specifying functional dependencies other than superkeys. Okay, so they doesn't provide a direct way of specifying FDs other than superkeys, having superkeys. Now we can specify FDs using assertion, but they are first of all out of our scope, and these things are currently not supported in any given product in the market having a SQL engine. Now, even if we had a dependency preserving decomposition, Using SQL, we would not be able to efficiently test a functional dependency whose left-hand side is not a key. So even if we had a dependency preservation decomposition, SQL would not be able to efficiently test FD. Okay, so we need to keep these problems of SQL in mind while doing the design thing. So our goal is to have a relation in BCNF and ensuring lossless join and dependency preservation while doing decomposition. So we will move to multi-value dependency in our next lecture. Till then, thank you.